Okay. So my talk is kind of fitting well in the theme set by Stefano Bianchi earlier, because I'm going to address another challenge to the standard AGM paradigm. And in fact, I think it complements it well, because in the slides he skipped, I think I glimpsed some images that he was intending maybe to touch on this issue. So this is the work done in collaboration with Daniel Asmus and Konrad Tristan at the European Southern Observatory in Chile. So thanks to Jaron and Stefano, I don't need to go over this picture in detail again. I just want to bring to the focus what is relevant for this presentation, and that is this toroidal structure of dust, often referred to as the dusty torus, which has a crucial role in the AGN unification model, because it accounts for the different appearance of the different AGN types. It absorbs the light from certain light sites from the central accretion disk and re-emits it in the infrared, so at the same time it accounts for the observed infrared emission. However, this structure is too small to be resolved, so the reason why we model it as the shape of the torus is because, as Stefano pointed out, it is the simplest geometry that can that fits the paradigm. So it explains the type 2 and the type 1 and type 2 AGMs, and allows for the broad lines to appear in the polarized emission in type 2s. However, recently we've been able to start resolving some of the nearby sources with the help, with the advance of the mid-infrared interferometry, in particular the MIDI telescope on the very large MIDI instrument on the very large telescopes in Chile. So in these top two panels, what you see is our kind of the brightest, the nearest and the brightest type 2 AGN. They're like prototypes for the type 2 AGN, so those are the ones that we see edge on, so the view of the central engine is blocked. And what was found was quite surprising. So this here is the AGN in Circinus galaxy, and let me see where to begin. So what you see here in these two kind of disk-like components is not really an image, but kind of the image reconstruction based on the observed interferometric visibilities. So you see one narrow component in this direction and another wider perpendicular to it. This doesn't mean that they're actually in the shape of the disk. This is simply the simplest toy model of a 2D Gaussian. So this is just telling you there is one narrow component in this direction, another in this direction. These blue lines are indicating the ionization constant in optical, so the narrow line region. So what you would expect is that the dusty torus is oriented perpendicular to it in this direction. But what is interesting, in this direction we see only a thin component that is contributing only 20% of the mid-infrared flux, while the majority of the flux, 80%, comes perpendicular to it. So it seems like the torus is missing, and in fact, co-spatial with this narrow component is the Maser disk observed, indicated by this broken line. So it's a warped Maser disk with almost perfect equatorial motion. So we know that this is in fact a thin disk seen edge on. So instead of the dusty torus, we have a very thin disk, and then the majority of dust emission is coming from the perpendicular direction, from the polar region. Then it's the similar case, a bit more complicated picture, but similar case in 1068. These are two more examples. Basically, these are just a different representation of this kind of modeling. So in total, up to now, we have 5 sources in which the major fraction of dust emission is coming from the polar region. That doesn't sound like a lot, but actually the total sample observed with the VLTI MIDI is 23. And out of those 23, only 7 of those sources have good enough coverage in the so-called UV plane and signal to noise to allow you to infer, to say anything about the morphology of the emission. So for most of them, you can only say there is so much flux in the resolved component and this much flux in the unresolved, but you cannot say nothing about the direction. So only 7 of those are with good enough data, and out of those 7, 5, and from some colleagues who are working now on some new data, I hear there will be most likely another confirmation, so 5 or 6 of those 7 are having this peculiar dust emission in the polar region. So up to now we were talking only about the scales of a few parsecs, but recently we started seeing this polar elongation even in single dish observations on larger scales from few parsecs to few tens of parsecs. This slide here is from the last year work led by Daniel Asmus, where they look at a sample of mid-infrared images. The starting sample was about more than 100 sources. It turns out only 21 of them have, again, good enough data to be able to tell you something about the morphology of the emission. And out of those 21, 18 of them have this extended dust emission, again, not from the direction what you expect from the dusty torus, but perpendicular from the polar region. So 5 or 6 out of 7 on the small scales and 18 out of 21 on large scales. So this is quite contradicting to our standard Aegean dusty torus paradigm. So in the remaining of the talk, I will focus on this famous Aegean Circinus galaxy. So the image you see here was obtained as a Daniel Asmus by PI last year in the science verification program of the recommissioned Vizier instrument. Vizier is a mid-infrared spectrometer and imager at VLT, which was substantially upgraded and recommissioned, and now it has superior capabilities as you can see from this image. So this was observed in almost perfect conditions with seeing of 0.4 arc seconds. So you can see that we are here limited by the diffraction as evident by the pronounced iron rings. So what you see here is unresolved core, which is on the scale I think about few or 8 parsecs. But then what is peculiar, you see this bar-like feature extending up to 40 parsecs on each side of the nucleus, and again perpendicular to what you'd expect of the orientation to the dusty torus. So these are the all observations we use. This is the image I showed you before, just in a different color scale. So the 12 micron image, this is another image acquired in the same program at 8 microns, and these two images at 10 and 18 are from archives from the old Vizier. So all of them are showing this bar-like feature, and which is even more evident after you subtract the PSF. So this is the images of the PSF subtracted, so you can, we don't have a perfect model for PSF, of course, so you can see still some residuals which are artificial, but this bar becomes very, very obvious. So a bit more than a year ago, I spent a couple of afternoons with Daniel Asmus, who invited me to examine these images together. So in this slide, I am summarizing all the relevant observations, so the Vizier 12 micron image here, and then when you zoom inside with the interferometry, you see these two components. The disk component was spatial with the master disk, and the polar component with major fraction of flux. And then on roughly the same scales as the Vizier image, we see the ionization cone in optical. We see this north cone, the south cone we do not see because it's obscured by the disk of the host galaxy, but actually we can see it in polarized near-infrared light, so we know it's there. And if you would overlay this image here, the ionization cone would fit right about here. So what is interesting first is this component in Vizier is roughly have the same orientation as this polar component seen by MIDI, so they are likely represent the same physical structure. Another interesting thing to note is that this bar is almost perfectly aligned along the edge of the ionization cone. So we immediately thought that this would be edge brightening effect, so the wall of the cone is dusty, and then simply in this direction you have more emitters, so you start seeing this edge. But then the question is, why don't we see the other edge of the cone? So this should appear as an X-shaped structure. And this was puzzling us for a while when I realized that actually the answer is already there. All the clues are there, you just need to put them together. So if you pay attention closely to the macer disk, indicated by the yellow line, it is warped. So you have the dusty disk, you have the macer disk is warped, and then within this central part of the macer disk is the accretion disk, which is illuminating the whole structure. So if you would draw the axis of the accretion disk, so perpendicular to the disk, it would be pointing again almost exactly along the edge of the cone. Now the accretion disk, by the definition, has some kind of anisotropic pattern, so it is emitting the strongest in direction perpendicular to it, and then less and less as you go to its equator. So putting this all together in the same picture, so we assume that the wall of the cone is dusty. We have the anisotropic accretion disk with orientation following the inner part of the macer disk. The blue arrows indicate the anisotropic emission pattern, which is here a bit exaggerated just to make it obvious. So, but the main point is, which you probably already guessed, is that such an anisotropic accretion disk would illuminate very brightly this edge of the cone, while it would send very little photons toward the other edge of the cone. So you could expect this structure to appear like this. So this is actually the temperature, the cut in the vertical plane of the model, which I will present in a moment, where you can see that indeed this edge of the cone is much hotter than the other one. So this seems like a nice idea and fits the picture, but of course we wanted to confirm it with the detailed physical modeling using this skirt code that I mentioned earlier. So it's a code-based, transfer code based on the Monte Carlo technique. I'll just very quickly explain what's happening. So in MCRT simulations, what you do is you define the geometry and optical properties of the dust. You define also geometry and spectral energy distribution of the primary source, which in this case is the accretion disk. Then from the primary source you send out a large number of photons in different directions. You follow each of these photons along their path, and when they encounter a dust particle, you use some proper probability distributions to determine what will happen to the photons, whether they will be absorbed or scattered, and scattered in which direction. So you're collecting all these photons with virtual instruments, and at the end of simulations you can reconstruct the image of your source and their spectral energy distribution. So this is one such an example of the classical dusty two-phase torus in Agon and Faison and their corresponding SEDs. So what we wanted to do, we wanted to test several geometries that could possibly explain these observations. So the first two is kind of what we would expect, like so we have the compact inner disk and then the large-scale cone, or the cone could be in the shape of hyperboloid, which is effectively the same at large distance, but maybe more realistic in this inner region. Then another is the shape of paraboloid walls, so paraboloid shell. And finally, we wanted to test if the classical torus, dusty clumpy torus, could still explain the observations, because if you assume that the torus is surrounded by some low-density ambiental dust, then simply by collimating the radiation, you might expect it to produce such a bar-like feature. So these are the images of different inclinations. What is relevant here is the third row, so it's the edge on view. And you can see that all of the models seem to have potential. They are all showing this asymmetric emission and might produce the observed bar. But to really compare it to the observations, we need to simulate how these molecules would look if they would be at the distance of Circinus galaxy and observed with the Vizier instrument. So we did this by rescaling the pixels of the model images to match the pixel size of the Vizier instrument. Then we convolve it with the corresponding PSF, including also the same level of background noise. So what you see here, these are the observations I showed you earlier at different wavelengths. In the first and the last row are our model images. So this is the case of the Quantum torus surrounded by a sphere shell of dust. In the top row is the case of the accretion disk aligned with the system axis, and the bottom row is accretion disk tilted by 40 degrees as indicated by the rotation of the maser disk. And these here are their corresponding simulated observations. So we can say that we can really rule out this case as it produces a prominent bar only at 18 microns, but it is much wider than the observed bar and with a completely wrong orientation. So we can really exclude this case. Next is the paraboloid shell model. Again, line disk and tilted disk. We can exclude the aligned case because it results in the kind of X-shaped structure which is not observed. For the case of tilted disk, we seem to be having a similar bar, but unfortunately it's not quite obvious in the projected image here. But the bar is actually, you can see the warp in the bar and the change of the orientation due to the curved walls of the paraboloid. So this case, although a bit promising, is not really working. And then finally the case of the hyperboloid or cone wall. Again, aligned disk can be excluded, and the tilted disk seem to qualitatively produce indeed the bar as we observed. So we focused further only on this model, and we generated a large grid of models varying the parameters of the disk and the cone wall, and we compared the resulting SEDs to the compilation of SEDs we found in the literature. So what you see here is these red triangles is photometry extracted from small apertures. So they would correspond to the unresolved nucleus, so they can be only taken as a lower limit. This orange line here is the VLTI MIDI spectra, which is again small aperture, so only a lower limit. The cyan circles and the spectrum here from Spitzer and from different instruments like Vizier and T-Rex and so on. So they are corresponding roughly to the total aperture of the Vizier image, so this is the one that we want to match closely. And I don't think I have the time, but I'll just mention that we know from these earlier observations by Roche et al. That there is a significant foreground absorption by the dust in the closed galaxy, and based on the depth of this liquid feature we can get an estimate of how much the absorption is happening in the foreground. So we took that into account, and to our models we applied the corresponding extinction maps, and this solid black line is the final model, so with the extinction included, and you can see that we have a very good match with the entire SED. So these are the corresponding, so again the observations, the PSF, or model images and simulated observations, and you can see we have a quite good match at all wavelengths. Then we went a step further, and what we did is from these images we made kind of a mini SEDs, so we extracted photometry for different positions, for different apertures along the bar and perpendicular to it. So this here is the SED from this central aperture, and then to the north and to the south, and here to the east and to the west. You can again see that we have quite a good match in the inner region. In the farthest position there is a mismatch, particularly at 18 microns, but that's because these positions are simply just dominated by noise and PSF. Also in this direction we have a good match at most of the position, and a bit less good match on this side, but that is because of the very strong absorption. So the actual foreground absorption has a stronger gradient than what we assumed for extinction maps, and we could tweak the map to match this, but it wouldn't bring anything into the model. Okay, so maybe I will just very briefly say, so now we are quite convinced that this dust in polar regions isn't really there and common. So how did it get there? Where there is a bulk of theoretical works that are showing that the radiation pressure from the accretion disk and the dust grain can drive very efficiently this dust grain into the polar regions, leaving behind the so-called dusty torus, or in this case only the thin disk. And then I will just mention that in the follow-up work in preparation now we are also doing this detailed modeling of the interferometric data, so we are simulating how our model will look like observed with the VLTI MIDI, and it's still in progress, but we already are having quite a good match with the visibility, so we are confident that it will be consistent even with this data on the small scales. And then something I started doing very recently is I was calculating the polarization, optical polarizations for these different models. So here you have the polarization vectors overplotted over the flux images, where the rotation of the vector is of course the polarization position angle, and the length of the vector is the polarization degree. And these plots here are the integrated polarization along the y-axis. So for these three different models, so hollow cone, paraboloid shell, and the torus with the spherical shell, for the case of the accretion disk aligned with the system axis and tilted. And the good news is all of these models, and even the cases between the tilted and non-tilted disk, produce very different polarization signatures. So just a few weeks ago we submitted a proposal to observe this with polarimeter at the VLT Force 2 instrument. And if we get time, we should be able to get independent confirmation of the model we proposed here. And yeah, I should be wrapping up. I just want to say that we have a number of already approved programs. So a couple of months ago, we observed the Circinus again with Vizier, but this time with chronograph and sparse aperture masking mode, which allow us to get even sharper image and to start seeing more structure in there. And also in two other programs, we are observing those 18 AGNs which have the polar dust emission, but now with the recommissioned Vizier instrument to get even sharper and better images. And we are also observing 9 nearby type 2 AGNs, which we believe should show this polar dust emission itself. So there is plenty of going on, and I will conclude by saying that so for our prototypical AGN in Circinus, it turns out it's not so prototypical as well. We show that it's with infrared morphology and SPs can be explained well by a model of a small compound dusty disk and a large hollow dusty cone, which explains the morphology, SED, and the result photometry. And having in mind that, well, it seems that the major fraction of the sources we can resolve is showing this kind of emission in the polar direction. This calls for caution when using the standard torus models to interpret the data, and some of this work might need to be revisited. That's all I wanted to say, I think. Yes, thank you.
Questions? Very impressive work. I really like it. You are right. I want to talk about these torus, and I should like it. We didn't have time to do that. I have a question and a comment. The question is that if you have a look at the Chandler's images, because they will give you information on the dust content, which would be interesting and complementary to the dust.
Yes, we are not really, but we are planning to do soon with the colleague Claudio Ricci. What I know is that there is a very significant, extended X-ray flux up to
is very complex and extended.
Yeah.
You should also have 68.
Yes, yeah.
They are very close by, so they're very interesting. So you are planning.
Yeah, that's on our plate as well, yeah.
The comment is something that I wanted to say is that another possibility to test these things related to the X-ray part is to use X-ray polarimetry. But
Yes.
of course, with the first generation that we fly soon, it's out of reach, this kind of analysis.
Yeah.
Maybe in the future it will be very interesting.
Yeah, absolutely.
More questions? No. Okay, let's thank you.